Hello and welcome back. In section 1.6, we get to do a quick little mini review on logarithms. So first, our little Rosetta Stone translator. Log base b of y is equal to x is equivalent to having the statement b to the x is equal to y. In other words, the base stays the base. The other two things will sort of trade sides with one another, translating between the two. So as you can see, a logarithm is an inverse of an exponential function. Therefore, the domain and range will switch. So domain of exponential, recall, was negative infinity to infinity. So that implies that then the range of logarithm is negative infinity to infinity. Here we're going to make the same assumptions about b that we did last time. So b is positive and not worth 1. When we had the range of the exponential function, recall if I have a positive base and raise it to a power, it's going to stay positive. It'll never reach 0, but it can get very close to 0. And it can get as big as we need it to. So that means that the domain then of a logarithm is 0 to infinity. That's going to come in handy later on to know that. All right, so to solve these, we solve by translating. So for example, if I have the log base 2 of 16 is equal to x, I can say that 2 to the x power, so the base stays the base, the other things trade sides. So 2 to the x power is worth 16, and 16 just happens to be 2 to the 4th, so x is 4. And recall, 2 does follow the rules for base b. If b is equal to 1, we can't use this property anymore. All right, so hopefully you have done some logarithm work recently in your college algebra class. So what I'm going to recommend is trying out matched problems 1 through 3 in your textbook, page 75 for the current edition. So go ahead and pause it, find those if you need to, and then we'll try them together. Okay, welcome back. So matched problem 1 had 3 parts to it. So the first part, they wanted us to go from logarithmic to exponential. So they gave us the log base 3 of 9 is equal to 2. So the equivalent exponential would be base stays base, other things trade sides. So 3 squared equals 9 is our equivalent exponential. They also gave us a statement that the log base 4 of 2 is 1/2. So 4 to the 1/2 power is equal to 2, which of course is true as well. Remember, 1/2 power is really saying square root. So the square root of 4 is 2 is correct. And finally, they let us play with the log base 3 of a fraction. 1/9 is equal to a -2. So notice the output is allowed to be anything we want. We just can't have a negative in our argument. So the equivalent would be 3 to the -2nd power is worth 1/9, which is of course true. 3 to the -2nd is 1 over 3 to the +2nd, which is 1 over 9. Match problem 2, then we're just going exponential to logarithmic. So we had 49 is worth 7 squared, so the log base 7 of 49 is 2. So we're just using our Rosetta Stone here. They give us 3 is equal to the square root of 9. So we had one extra step in that square root. We had to turn into an exponent of 1/2. And after that, the rest of it's the same. So log base 9 of 3 is worth 1/2. And then our last one in match problem 2, 1/3 is 3 to the negative first. So log base 3 of 1/3 is -1. And in matched problem number 3, we were asked to actually solve. We had y is the log base 9 of 27. So in exponent form, 9 to the y is worth 27. 9 is 3 squared, so we have 3 squared to the y equals 27 is 3 cubed. Power to a power, remember your shortcut is to multiply, so 3 to the 2y is 3 to the third. Base is not negative, nor is it worth 1, so the exponents have to be equal to one another. So 2 to the y is worth 3, so y is 3/2. Our second one that we're solving, log base 3 of x is -1. So 3 to the -1 is worth x, so x is positive 1/3. So remember, your base was a positive, your solution will be a positive. And last one that we're solving, log base b of 1,000 equals 3. So b cubed equals 1,000. So b cubed, 1,000 is 10 cubed. So base had to be a 10. And then we get to play with a couple properties. Log base b of 1, we'll just say it's equal to n for the moment, and we'll figure out what n would have to be. An equivalent exponential, b to the n power is equal to 1. So it's basically asking us what power can I raise something to always end up with 1 as my answer. That would be the 0 power. So a general property from that, log base b of 1 is equal to 0. Next we look at log base b of b. Again, we'll put in a placeholder variable of n. So b to the n is worth b. If I don't have an exponent, I'm always allowed to raise it to the first power, so n is equal to 1. So then we can say that the log base b of b is always going to spit out a nice pretty 1. Next one, we get into just a short proof, not quite as detailed as we would do in, say, a Calc 1 course, but business calc, we can do a little proof there. So we're looking for what property this has. So for this one, I'm going to need a couple let lines. I'm going to let log base b of m equal c1, log base b of n equal c2. So then our equivalent exponential statements, so translating each of these directly from logarithmic to exponential, b to the c1 power is worth m, b to the c2 power is equal to n. So then b to the c1, b to the c2 is equal to m times n. Multiplying with the same base, our shortcut is to add those exponents up. So b to the c1 plus c2 is worth mn. So then we can translate it into logarithms. Log base b of mn is worth c1 plus c2. And then we can use our substitution. Log base b of Mike times November, C1 gets replaced with our let line. Log base b of m plus C2 gets replaced by what C2 is the same as, log base b of n. See if you can show the same kind of idea for the log base b of m over n. Just as a hint, your let line will be exactly the same as it was before. Just instead of multiplying m and n together, we're going to have m over n instead. So go ahead and pause that, see if you can finish that proof. Okay, welcome back. So log base b of m is equal to C1, log base b of n equals C2. And then instead of looking at m times n, we'll look at m over n. So m, recall, would be b to the C1. B to the C2 is worth n. So we have b to the C1 over b to the C2. So b to the C1 minus C2. So we're dividing with the same base. The shortcut is to subtract those exponents. Picture like an x to the 7th over x squared. That would give you an x to the 7 minus 2 or 5th power. We're doing the same thing here. We have the same base, so we subtracted those exponents. So then we just translate into a logarithmic statement. So log base b of m over n is C1 minus C2. And then you can finish it off with substitution. So C1 is still log base b of m minus C2 is still log base b of n. So multiplication turns into addition, division turns into, unsurprisingly, subtraction. A little corollary to the multiplication one. Corollary is just an immediate result. Log base b of a to the c power is log base a, or I'm sorry, base b, log base b of a times dot 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 times a. So we have an ellipsis in there saying that pattern keeps going. And this has c factors of a. Well, by that product rule, then we can say that this is log base b of a plus log base b of a plus dot 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 plus log base b of a. And now we have c terms. So then log base b of a to the c is c times log base b of a. In other words, the exponent turned into a factor. So we'll have a simplify, sometimes they'll call it expand. We'll do log base r of x squared y over zw to the 4th. So first I'll take care of that main division bar. So log base r of x squared y. And remember, division turned into subtraction. Minus log base r of zw to the 4th. multiplication turned into addition. So we have log base r of x squared plus log base r of y minus the quantity log base r of z plus log base r of w to the fourth. So then the only things to do, distribute the subtraction sign and make any of those exponents into factors. So then I can say log base r of the quantity x squared y over z w to the fourth will turn into 2 log base r of x plus log base r of y minus log base r of z minus 4. So the minus because we distributed, the 4 because we had the exponent, minus 4 log base r of w. So that would be our expanded form. Okay, so one more handy little tool to have. We'll do b to the log base b of x. Again, we'll temporarily let that equal n. If I switch that over to logarithmic notation, because technically we are in exponential notation, I have a base to a power, then the log base b of n equals the log base b of x. So then n and x, our arguments, will be the same. So the property then b raised to the log base b of x is equal to, by substitution, x. All right, so see if you can try the matched problems 4 and 5 starting in this edition on page 76. So go ahead and pause it, give those a spin, and I'll just pick out a couple to try out. Won't do all of them. Okay, welcome back. Let's see. So the match problem 4, they give us log base b of cap r over cap s cap t. So log base b of r minus log base b of the quantity st. So log base b of r minus the quantity, multiplication turns into addition. And then we distribute to finish it off. So log base b of r minus log base b of s minus log base b of t. The second one, similar idea, except now we'll have a 2/3 in front of both terms. Let's see, the third one, 2 to the u log base 2 of b. This factor I can turn into an exponent, so that's 2 to the log base 2 of b to the u. And by the property earlier on the page then, that is b to the u power. You do want to watch out for ones like the last one, log base 2 of x divided by log base 2 of b. I cannot turn that into a subtraction problem like we did with the first part of match problem 4. about the only thing I can do is turn that into one expression with the same base that is equal to the log base b of x, but that doesn't really help us expand it at all. That's just a change of base formula. Next problem number 5. We have 3 log base b of 2 plus half log base b of 25 minus log base b of 20 is log base b of x. So this, we're just writing the left-hand side as a single logarithm. So first we'll turn those factors into exponents. So we have then log base b of 2 to the 3rd power plus log base b of 25 to the half power minus log base b of 20 is equal to log base b of x. So we can do a little simplifying in there. So 2 cubed is 8. 25 to the 1/2 power is the same as the square root of 25, so 5. And remember, addition turns into multiplication, subtraction into division. So then this is the log base b of 8 times 5 over 20. And on the right side, we still have log base b of x. Base is the same on both sides, so the arguments are the same. So 8 by 5 is 40. 40 over 20 is 2, so 2 equals our x. Let's see, and we'll try some other bases. Natural log is another commonly used base. Recall that is base e. Hopefully you remember that from your college algebra days. So natural log of x plus natural log of the quantity x minus 7 is worth natural log of 30. So the left-hand side, I'll write that as a single logarithm. It was addition, so we'll turn it into multiplication. Same base on both sides, single logarithm on both sides, so now I can set the arguments equal to one another. And I can go ahead and distribute the left side. So x squared minus 7x minus 30 is 0. So that's factorable over the integers. If it starts as an equation, it stays an equation. Don't lose your equal to 0. Hang on to that. And we have a minus 10 and a plus 3. So x equals 10 or x equals negative 3. And for this much of the problem, we get to keep both of them. But recall that the domain of a logarithm was 0 to infinity. Substituting negative 3 in for this x here, I get a negative. That is an extraneous solution. Natural log of 10 is a nice, neat, pretty real number. Natural log of 3, a nice, neat, pretty real number. That one we get to keep. All right, so we'll try a couple other solving ones. Log of x is worth 7. Again, this one, just like natural log implies base e, log without a base written, it's implied that it is base 10. It's just understood to be base 10. So then I can say that 10 to the 7th is equal to x, or x is a 1 with 7 zeros. $10 million. They could ask us to solve log base 3 of x equals 7. So 3 to the 7th is equal to x. And that one, if you want to plug and chug, get the longer version of the number, the exponential form should be sufficient though. Let's see, natural log of x is equal to 12. So again, if they use the natural log, that's understood to be base e. So e to the 12th is equal to x. I think your author will sometimes ask for a decimal approximation for these. I would prefer the exact value. Similarly, for e to the x is worth 9, we can translate into logarithms to get that exponent out of, or a variable out of the exponent. So natural log of 9 is equal to x, and that's our exact value solution. Your author will also ask you for an approximation. I'm not interested in the approximation. I like the exact. Similarly, for like 2 to the x is worth 75. So we can say log base 2 of 75 equals x. If it's an application problem, that's when an approximation would make sense. But if they're asking just to solve it, I'm looking for the exact value. All right, so let me have you all try a couple out. So see if you can try match problem 8 through 10 on number 10. A little hint there. Compounding continuously. If you don't recall that from your college algebra days, new amount is principal times e to the rate times time. That's for compounding continuously. If we're compounding anything but continuous, then the amount is principal times 1 plus r over n to the n times t. N is number of compoundings. R is the interest rate. Okay, welcome back. We'll go through some of these. I'll give myself a little bit of room to work here. So on 8, we have natural log of x is negative 5.062. So then e to the negative 5.062 is equal to x. I have the log of x is 2.0821. So 10 to the 2.0821 is equal to x. On match problem 9, let's see, we had 10 to the x equals 7. So then log of 7 equals x. We don't write the base if the base is 10. E to the x is worth 6. So natural log of e to the x is natural log of 6. So x is natural log of 6. We had 4 to the x is equal to 5, so log base 4 of 5 equals x. If you want, you can also use the change of base and call that x is maybe natural log of 5 or natural log of 4, or log of 5 divided by log of 4. Either one of those will get the same solution. This one is an exact value. These two will let you key in an approximation into a calculator in case you're doing a word problem. And then on the 10th, let's see, we're doing the tripling time. We're looking at 13% compounded annually. So if we're tripling our initial investment, our new amount would be 3p. So 3p is worth p times 1 plus interest rate 0.13 over once a year to the n times t once a year for t years. So the p's will drop out, so 3 is worth 1.13 to the t. If this is not a nice, neat, pretty number, bring this whole thing as you see it along instead of rounding it. Do not round this value. This one, they gave us a nice, neat, pretty one that ended. So then the log base 1.13 of 3 is equal to t. So t is natural log of 3 over natural log of 1.13. And then we can plug and chug that in the calculator. And our answer will be in years. So natural log 3, close it up and divide by natural log of 1.13. Close that up. 8.98898, blah, 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 blah. So if you are keying that into your calculator and you're saying 3.2000 whatever, you're missing a parenthesis. So it will take 8.99 years to triple the investment. So notice they didn't even really have to tell us what the investment was. Was it $1? Was it $1 million? Was it $57.32? All of those will take the same amount of time to triple the initial investment. So it's independent of what P was, and that's because that cancels out on this step. Okay, so some problems to try out from section 1.6. I would try out 1 through 37 on the odds. 47 to 55 also on the odds. 61, 63, and 83. If you have any questions, please get in touch. Otherwise, I will see you next time. Stay safe out there.